Hello everyone, I'm Jianchang Su from UConn. I'm excited to present Runtime Attestation for secure LLM serving in cloud-native trusted execution environments. Large language models are now everywhere, and they are overwhelmingly deployed in the cloud use Kubernetes and containers. This parallel, while scalable, creates a major security problem. When you serve an LLM in the cloud, your most critical assets, the model weights, user queries, and generated response are exposed to the untrusted infrastructure. A malicious administrator or a compromised host component could potentially steal your data or tamper with your model. Confidential computing technologies like Intel TDX promise to solve this with hardware-based isolation. However, current solutions are incomplete for the cloud-native LLM. First, they offer only boot-time attestation, meaning integrity is checked at launch but not during the runtime, leaving the system vulnerable to post-boot attacks. Second, they lack container awareness, protecting the whole VM instead of individual microservices. Third, Kubernetes is obvious to security state of its node and cannot make trust-based scheduling decisions. Finally, solutions are often tied to single TE vendor, creating hardware locking. To fix these issues, we present a comprehensive framework that creates an unbroken chain of trust from hardware to application. Our solution has four key paths. First, we enable runtime attestation for contiguous integrity verification. Second, we provide container level security with fine-grained measurements for each container. Third, we integrate directly with Kubernetes for attestation-aware scheduling. And fourth, we offer hardware-agnostic API to prevent vendor locking. Our goal is to enable LLM deployments that are secure and portable and continuously verified. Our threat model focuses on protecting critical assets, the LLM model's sensitive user data, and the runtime state. We define against the three main adversaries: a malicious cloud infrastructure, a compromised Kubernetes orchestration plan, and malicious containers on the same node. Our world does not address the physical attacks or the inherent algorithm vulnerabilities in the LLM itself. Here is our system architecture. At the bottom, we build on a hardware TE like Intel TDX. Inside the confidential VM, we extended Linux Integrated Measurement Architecture, or say IMA, to continuously record measurements. We then provide container level awareness to connect everything to Kubernetes through constant daemon and plugins. This design creates a verifiable trust chain from the hardware all the way up to the orchestrator application. The core problem with TDX is a boot time only attestation. To fix this, our first component introduced the runtime measurement register extension. This allowed the guest OS to securely record critical events, like loading a kernel module into hardware registers during runtime. Integrating this with the Linux IMA, we create an unbroken and verifiable chain of trust from boot time until shutdown, closing the post-launch vulnerabilities gap. To secure individual microservices, we need container-level integrity. Our solution is confidential integrity measurement agent, or we say CIAM. The CIAM make IAM container aware using Linux C groups, enabling separate measurement for each container in a VM. It measures container image layers during their life cycle and record this into our runtime registers. It also provides a gRPC API for container to request their own attestation report. Because of this delivers the fine-grained security need for modern microservice architectures. Standard Kubernetes is not security aware. We solve this by making it attestation aware. First, a constant admission webhook verify the container image integrity before it deployed. Second, our TE-aware schedule plugin ensure the workload are all in place on the verified trust node. Finally, an attestation policy engine allows the administrator to define trust-based rule as code. Together, this component prevents orchestration level attacks and enforce the security compliance. To prevent vendor locking, our final component is hardware-agnostic API. Applications written for one TEE, like Intel TDX, typically don't work with other like AMD SEV. Our API provides a single high-level interface for the common functions like gap measurement and gap quarter. Underneath, adapters translate this code from for these specific TE technologies being used. This design enables portable, future-proof confidential applications. In conclusion, we were showing that current security models and methods are inadequate for cloud-native LLM serving. Our framework addresses the critical gaps by delivering a comprehensive end-to-end security solution. We provide contiguous trust through the runtime attestation, granular security at the container level, intelligent orchestration by making Kubernetes trust-aware, and cross-platform portability with the hardware-agnostic API. We believe this approach will significantly enhance the security of deploying sensitive AI workload in the untrusted environments. Our system has no limitations. It does not mitigate the side channel attacks, which remains a challenge for all TEs. The contiguous measurement introduces the performance overhead that needs to optimization, and the periodic nature of the attestation leaves a small window of risk. Our future work will focus on a full empirical evaluation, performance optimizations through event-driven triggers, and extend the framework to secure distribution inference across multiple nodes. Thank you. If you have any question, please contact me by this email.